today we are going to look at something called Lami's theorem. I'm not sure, do you guys do Lami's theorem in physics?
No, we don't.
Okay, well, this is something, like I've stated there, this is extension work, right? It's not required, right? You don't have to be able to do this. You can continue resolving forces like you've been resolving them before by splitting them up into components. However, right, this does provide more efficient techniques if you have three forces in equilibrium, right? So the important thing here are three forces and they must be in equilibrium, right? It's going to present a unique opportunity for us to use previous knowledge to help us solve these problems maybe a little bit faster. Okay. So let's just remind ourselves that force is a vector. A vector has both magnitude and direction. So I've got four vectors over there. So maybe that's four forces acting on a particle, the particle being right in the middle, right? And we know that vectors can be combined, right, to create a flow of what's going on, right? And when basically vectors are in equilibrium, right? In other words, if you have a net effect of 0, right? If this object being held in position like that is stationary or at constant velocity and in equilibrium, then we can line the vectors up and they should basically end where they start. Okay? And that's true for no matter how many vectors you have. You could have 1,000,000 vectors. If you have no net force, right, or you have a net force of 0, that means that you could actually line your vectors up end for end, and they should end where they start. Right? So what we'll do is we'll take these vectors over here quickly, and just for some fun, I'll move them around. There we have vector 1. Let's move vector 2, right? And this is what we mean by putting vectors end to end. And we will take the last one, and hopefully they should line up. There we go. Right? So if we have something in equilibrium, the vectors will line up and we can create this shape, right? Where the vectors will create some kind of perimeter of some shape. Now, this is only going to be the case where your vectors have the exact, or the net force is exactly 0. Right? So if I had to change any one of my vectors now and make any one of those vectors smaller or bigger, or change the angle at which the force is being applied, then those lines would not add up. Right? They wouldn't make a nice little shape like that. Now, this is obviously very, very nice, okay? Because when we have three force vectors in equilibrium, we are presented with a lovely opportunity, right, to use some trigonometry, right, to make these more complex problems easier. Right? And this is unfortunately provided, very importantly, we have enough information. Okay? We need to have enough information in order to still solve this way. So for those of you that just joined Toya Keanu, right, this is what we call extension work. You don't have to use these techniques. You can split your vectors into components and resolve the vertical and horizontal component if you're comfortable with that. This is just going to provide you with additional techniques to solve three forces in equilibrium. Okay? So when we have three forces acting on an object in equilibrium, right, what I'll quickly do is I'm going to move these forces around so that we can put them end to end and see what happens. Right, so we'll start, I'll just start with any random one here. There's vector C, there's vector B, here's vector A. And when I line them up, you'll notice that I create a triangle. Right? Now, we have some very powerful tools, right, when we are working with triangles. Right? We spent an entire term last semester looking at trigonometry. Okay? And so we can use things like the sine rule and the cosine rule to help us resolve these vectors faster, all right? So by drawing this triangle of forces, we can use the sine and cosine rule directly without having to resolve components. Okay? So in other words, I have 3 force vectors there, right? You might have the value for 2 of those vectors. You're being asked to resolve and find the final vector. Now, usually that would require you choosing a line of action, right? Finding the vertical and horizontal components, and then combining them to find the vector. What we're saying is that if you combine these 3 vectors in equilibrium and you create this triangle, the magnitude, right? Or sorry, the length of the side of these vectors is the magnitude of their forces. Okay. Everybody with me so far?
Yep.
Yeah.
Yeah. So we're just taking our vectors, right? And instead of resolving them, in other words, choosing a line of action, I'm now saying, well, let's combine these vectors end to end and create this triangle. Right? We don't actually have to create a triangle, right? Once we understand the concept of this, we can avoid having to make a triangle. Okay, there are some circumstances where it's going to be easier to draw a triangle of the forces, but sometimes you don't even need to do that. Right, now with trigonometry, we need to know also some angles. Okay, so I'm going to return back to my vectors over here, right? And now we're going to add some vectors and their angles in. So I'm going to choose, let's start with vector A. Okay? So you can all see vector A is this guy over here, and he's flying off in that direction to the left. Now, the convention is to label the angle, right? Right opposite vector A. In other words, this angle over here, you'll see it's the angle between the other 2 vectors, right? So the angle opposite vector A, right? It's not adjacent. These are the 2 angles adjacent to vector A. This is the angle opposite to vector A, right? The convention is to call this angle alpha. And then we have the vector right across, or the angle right across from vector B. And finally, the angle right across from vector C. Anybody know what the Greek letter for that is? No? No takers on what that vector is? That letter is? The Y, the Greek letter Y, what looks like a Y.
No, I'm not sure.
I can't remember. I was too lazy to look it up.
Isn't it gamma?
Like, yeah, it's gamma. Could be. Anyway, so those are the symbols that are usually denoted by these opposite the forces. Okay, but it doesn't matter. You can use any letters you like. You can even use little a, little b, little c to specify which angle you're talking about. So that doesn't really help us when we're looking at these, because remember, we want to now combine these into a triangle. So what I'm going to do is I'm going to move these angles, and I'm going to create my triangle. Right, and remember, when you are creating this triangle, you have to put the vectors end to end, right? So you can't do, for instance, well, you can, but it's going to make your life very difficult. You can't do that, right? You'll notice that that doesn't work. The arrows have to be pointing in the same direction. So where are my angles here, right? Because we've created now a new shape and the angles seem to be lost. So what I'm going to do is I'm going to extend, right? I'm going to extend this vector over here. Right? I'm actually also going to make it dotted so you can see that it's not the vector. Right, so just ignore the arrow. In fact, I can chop that off. And I'm going to move this in line with that vector over there. Now I want you to compare the two images, and I want you to see this is where angle beta was, right? And what I've done is I've actually just slid this vector, I've actually just slid it down in that position, right? Which means that actually here is that angle over there. And I want you to note its position relative to where force B is, right? So if the angle on the outside is beta, Zara, what's the angle on the inside going to be? Right, I have a straight line there. If the angle on the outside of that,
180 minus beta.
there we go. So this is just going to be 180 degrees minus beta. Okay? And we can do the exact same thing for all of the other vectors if we want. Okay? So we can extend the lines over there. Okay. And if we go look at and compare the two diagrams, we can see that this used to be angle alpha before I slid that vector down, right? And so the angle on the inside here is going to be 180 degrees minus alpha. But I want you to look where the 180 degrees minus alpha is and side A are. Okay, they are still opposite from each other. Okay, and obviously, unsurprisingly, if we do the same thing over here, so I will make this guy spotted again. We extend that vector B, right? We can see that this angle in here, this is just, as Zara said, angle gamma, okay? Which means the angle right on the inside here is 180 degrees minus gamma, right? So this is where our lovely rule, the sine rule, comes in. So I'm going to write the sine rule out, right? I'm sure you all remember us. A over sine A equals B over sine B equals C over sine C. So let's write, we've got A over sine A. We should actually use little a there. Right? Little a being the side and big A being the angle opposites. Right? I hope you guys still remember the sine rule. B over sine B, C over sine C. Now that's the sine rule. Let's put in the angles from our triangles, okay? Because this is a triangle, and using the sine rule, it's saying that the side length divided by the angle opposite that side, they are all in perfect ratio with each other. That's why they are all equal to each other. If you don't remember the sine rule, then I strongly suggest you go and revise it, okay, from IGCSE. Okay, let's look at our triangle. The side length for our triangle is the size of that vector, right, which is just its magnitude, and it just happens to be A, right, in my example. The angle across from A, right, we've worked out as 180 degrees minus alpha. Right, side length B, which we can just use as force vector B. And we have 180 degrees minus beta, all right? So the angle directly across from this vector, this is the vector here, and the angle directly across from it, opposite from it, is that angle on the corner, all right? These angles here, these are angles adjacent to B, right? In other words, adjacent means they are also on line B, right? The angle opposite is the angle that B does not touch. And finally, we have vector C, and the angle in that triangle opposite to vector C happens to be 180 degrees minus gamma. Right, Twaya, let's rewind our brains to how many months ago? 2 months ago.
Yeah.
The sine of an angle 180 degrees minus theta, what is that equal to? I'm going to draw a little picture for you. Maybe it'll help you remember.
Oh.
Where is sine positive? Well, anything less than 90 and anything less than 180 degrees, sine is positive. So 180 degrees minus theta, right? Sine of 180 degrees minus theta is just the same as?
Positive sine.
If this is theta over here,
yeah,
this is just 180 degrees minus theta. And we learned that in trigonometry, right?
Yeah.
That this is just the
I
same
remember.
as sine of theta. Right? Which means if you have a look at our equations there, all of those are 180 degrees minus something, right? And I've very naughtily forgotten to put sine in front of all of those angles there. Right? This is the sine rule, so it should be sine of 180 degrees minus alpha. Very naughty, Mr. James. Sine. Right, and if since sine is positive in the second quadrant, right, and you know graphically as well that anything above 180 degrees for the sine function, right, if we had to draw the sine curve, sine of theta and sine of 180 degrees minus theta would give you exactly the same value. So we can change all of those into the simpler A over sine alpha equal to B over sine theta equal to C. Now, if we return back to our original diagram, right? So this is not the triangle. Have a look at the original force vector diagram. Remember, we're looking at forces, not at triangles, right? If we knew the angles or we knew the magnitude of the forces, right? Have a look at the sine ratio and look where the angles are, okay? They are still, there's vector A, and the angle opposite vector A is the angle from my equation, right? So I don't have to go and draw the force triangle if I can understand where the angles are and where the vectors are. Which ones are the ones in relation to each other? Right? Does everybody see where the angles are compared to the magnitude of the vector that relates to it? So this discovery, this is Lami's theorem, right? And it states that a particle in equilibrium with three forces acting on it, the ratio of the magnitude of the force with the sine of the angle between the two forces is the same for each force, right? Because remember, the sine rule is just the relationship between the size of the length of the triangle and the angle opposite to it, right? And if we extended those triangles out and create our vector, because sine happens to be positive in the second quadrant and the sine of 180 degrees minus theta is the same as sine, we are able to use that information or that discovery and now help us solve problems faster. How are the brains? Are the brains okay?
Brains are doing
Yeah.
okay.
Yeah. Do you understand what's going on here?
So.
Yep.
Okay. So again, remember this is an extension topic, right? If you don't like this, you can go back to resolving forces by choosing a line of action and resolving forces vertically and horizontally, right? But let's do an example to see where the power of Lami's theorem really comes out. Okay? So the first one we're going to jump into is this worked example over here. Now, funny enough, the very first example has nothing to do with the sine rule. Okay, so I want to remind you that when we use the sine rule, we have to have at least two sides and at least one angle opposite that side, right? So if you look at the sine rule, we don't have to compare all three. We just need, we can just compare two bits of the ratio. So say we're looking at sine A and sine, or A and sine A and B and sine B. You can see that in order to solve, right, we have four components, which means we need at least three of them, right? So either we need to know the magnitude of both the forces, and we need to know one of the angles opposite one of those forces. In other words, it can't be the angle opposite the third force, all right? We can solve for the unknown angle, and vice versa. If we know the size of the angles between the two forces and we know the magnitude of one of the forces, we can solve for the other force. However, we also have the cosine rule. So I've written the cosine rule up over there for you. A squared equals b squared plus c squared minus 2bc cos a, right? That's just a fancy version of the Pythagoras theorem for triangles that are not at 90 degrees. Okay? And the nice thing with the cosine rule is it can solve a number of things, okay, depending on what information we have. For instance, if we know the length of all three sides, or in our case, all three vectors, we can solve for one of the unknown angles. And this is the angle opposite side A. Okay? Again, if this is Greek to you, then it's because you don't remember the cosine rule. So let's have a look at this worked example and give it a go, right? So this is an object in equilibrium by the action of forces of 10 newtons, 8 newtons, and 9 newtons, shown in the diagram. Okay? and they want us to find angle theta, and they want us to find angle, is that a funny Y curly thing? Zara, what's the name of this guy? Anybody know that one?
I'm not sure.
I'll have to go polish up on my Greek alphabet by the looks of it. So the first thing we can do is we can quickly turn these forces into a simple triangle, right, to help better understand. So here's my 10 newtons force. I'm going to guesstimate. Let's make that a little bit longer. Come on, draw me narrow. There's my 8 newtons, and let's come back down. This is my 9 newtons force. I'm going to just move the value of the magnitude of the force next to it just to make life easy. Okay, so in the same way that we calculated the angles for the triangle previously, we can do the same thing here by just extending these vectors.
Mr. James, I think that it's delta.
Delta, okay. Right, now we need to compare where these angles are in relation. Now, once you kind of get the idea of where the angles are, you don't need to draw force diagrams. I'm just drawing them so that I can show you where these are coming from, right? So that I'm not making them up. Right? This angle here, right, is just the angle theta here. All that we've done is we've taken this 10 Newton vector and just imagine it's reversing and it's going down. It's moved down the line. Here's the line, it's moving down, right? And it leaves the angle behind. So this is just angle theta over here. And we can do exactly the same thing for angle delta. And we could do the same thing for the other angle, but we're not being asked to calculate the other angle at this stage. So I'm just going to do theta because we don't have really time to do the other one. But based on how I do this, you can just solve the other one yourself, right? Now, I want you to have a look at the information we have. We only have the size of all the vectors. We don't have any of the angles, right? However, that's very powerful because if we have the length of all the sides, we are able to calculate using some trigonometry the size of angle A. So let's have a go at this, okay? We want to find out the value for angle theta, right? But theta isn't inside the triangle. However, this angle over here is just 180 degrees minus theta, right? So we'll use that and we'll solve for theta later on. If I'm solving for angle theta, let's call that angle A, right? This is angle A over here. The side opposite angle A is little a, right? Side A. And we can just call the other two sides side B and side C. Now we can just go to our equation, the sine rule. So the sine rule is a squared equal to b squared plus c squared minus 2bc cos of angle A. Oh, goodness me. And then just fill in the information from our triangle. Side A is 9 newtons, so 9 squared. Side B is 10 newtons, so 10 squared. Side C is 8 newtons, so 10 or 8 squared. minus 2, B and C, so that's going to be 8 and 10. And this is going to be the cos of angle A. The cos of angle A is not theta, it's 180 degrees minus theta. And now we can just solve for theta. All right, you're going to get the cos of 180 degrees minus, right? You're going to get a minus number because remember cos is negative, right? And after crunching that, you should get 121.2 degrees. So there we are able to calculate the angle opposite. Right, now we have an angle, which means that if we were asked to find the magnitude of one of the vectors, we could now also do that. Okay, are we all happy with the cosine rule? I hope we can all still remember how to work with guys like that. Right, just use this thing over here. Right, go back to when we did trig and converting angles right into their, what was the word that we used? Their acute angles or their reference angles. Right, we'll quickly do this one as a final one. Right, there is another worked example, and what I'll do is I will make a separate video on that later. Right, it's just going to be, this example is just going to show you where you can use the sine rule, and the next example just shows you the comparison of using the component method where you split all the forces into their components to resolve versus using the sine rule. Okay, so let's quickly have a look at this. We have two angles and we have the length of one of the vectors that's opposite one of the angles that we know. And we've been asked to find the tension in the other two rows, right? Now, obviously, this is a circle, so we can actually, based on the information that we have, we can already work out what the missing angle is, right? It's just angles around the point. So this missing angle here is just 140 degrees. Now, usually you would have to pick the angle, you'd have to choose your line of action, you'd have to split all the forces into their two components, right? Except we can work this out much simpler by just using the sine rule. Sine A over sine A is equal to B over sine B. So let's find the angles. Let's start with T2. We want to find T2, and it's over sine of 120, right? Because it's the angle opposite from T2. Right? Let's go find a side and an angle that we know both of, right? That's going to be that 90 newtons. And the angle across from it is 100 degrees. And so T2 is just equal to sine 120 multiplied by 90 over sine 100. Your calculator will make short work of that, and you will get T2 equal to 79.1 newtons. So in two lines, we've resolved those vectors. Right? If you had to split them up into their components, you would have to pick your line of action, you'd have to see which components to split up, you'd have to take the vertical and horizontal, and then solve simultaneously if required. Okay? Whereas we've just done this in two lines. Right? And T1, we could do exactly the same. T1, right? The angle across from T1 is that angle we worked out of sine 140 degrees, right? And we can use that 90 over sine 100 again. Right, that's going to give you 58.7 newtons. So a much simpler way of resolving forces, right? But very importantly, remember they must be three forces in equilibrium.